Okay, so this is basically another way of using a polynomial to fit an equation, an exact fit. But this is, I would say, uh, is slightly more, well, it's more in the lines of Lagrange interpolation, where there is a sort of a pattern which emerges when you do this uh, for 2, 3, 4, 5 points, and so on. So what we'll do is here, we'll take a different approach. I'm going to show you that there's a pattern which emerges in computing the constants of a polynomial. Start with 2, then we'll go for 3, then for 4, and you'll see that that pattern helps us to generalize from, we can then just go to like 100 or so, whatever you want, just based on a certain pattern, which we will see. So it'll take me some time to develop and show you the pattern. So what we'll do is, I'm going to show this, start with the 2-point equation, and then go to 3 and 4, and then we'll just generalize it to n dimensions. So what we're going to do here is we are going to observe a pattern which will help us to generalize to n plus 1 points. Okay, let's start with 2 points. That is, you're given 2 points, and you are trying to find the best equation that passes through 2 points. And I'm going to just, instead of having y, I'll just call them x and f of x. So x, f of x, x1, f of x1. Now we know that if you want to connect 2 points in the simplest possible fashion, then you just draw a straight line between them. So what we'll do is we will just assume f of x to be, I'm just going to use a different notation just to distinguish that from polynomial fit. Okay, now I could write C0 plus C1x, but Newton, the same guy who knows many things, thought there's a smarter way to write this as C1 times x minus x0. Okay, so this is different from polynomial. If it was a polynomial, I would write C0 plus C1x. If it was Lagrange interpolation, I would write it, those x minus x0, x minus x1. But here, this is how you assume. You do not put x1, the second point, in the equation. Now, what you can do is, we need to compute C0 and C1. Okay, and C0 and C1 passes through the 2 points, x0, f of x0, x1, and f of x1. So what we'll do is, we'll sub in the value, C0 plus C1. Okay, so the whole point of doing this exercise of writing x1 and x0 is because when you put x equals x0, C1 basically becomes, C1 cancels off in the first equation, and you basically obtained C0 as f of x0. Now let's put the other point, f of x1 is C0 plus C1, x1 minus x0. But we do know what C0 is. C0 is what we solved from the first equation, right? So C0 is f of x0. And so what we can do is we can write f of x1 equals f of x0 plus C1 x1 minus x0. Which means we can now solve for C1. It is f of x1 minus f of x0 divided by x1 minus x0. Okay, in summary, C0 is simply f of x0, C1 is f of x1, f of x0, x1 minus x0. Okay, we'll just note that this is what we got by assuming for a 2 for a curve for the Newton divided difference when it passes through 2 points. Okay, now I'm going to take a step further and do this for 3 points. Okay, and then slowly we'll see that the pattern will emerge. So that would be x0, f of x0, x1, f of x1, and then x2, f of x2. So in this case, we need a second order polynomial because there are 3 points. So this is how we will assume the polynomial. It is c0 plus c1 x minus x0 plus c2 x minus x0 x minus x1. So again, you can see that the first 2 terms were similar to the ones we assumed for this one, exactly the same. The new term, the third one now, C2 has x minus x1. Okay, so let's see the consequence of assuming that particular formula. Let's sub in the values. That is, let's put these in the equations. So f of x0 is c0 plus c1. Well, that becomes 0. And then c2, this also becomes 0, which means c0 is f of x0. Next, f of x1 is c0 plus c1 x1 minus x0 plus c2 times 0, because when you put x equals x1 here, that term cancels off. Okay, so what I can do here is I can sub in the value for c0. It is f of x0 plus c1 x1 minus x0. Okay, so which means we can solve for c1. I just wrote down the 2 values we found, c0 and c1. Now, if you have been following what I've been doing here for this and the previous part, you'll notice that the formulas I got for c0 and c1 are not new. They're exactly the same formulas I got for the 2 point. So these formulas here you can try to match them up with what I had here. It's the same one, C0 and C1. Which means that now if you don't really need to do the calculations again. If you go from 2 to 3, it's the same formula, right? But here, remember, we have 3 things. We have C0, C1, and C2. So we need to still compute what C2 is. For that, what we'll do is we'll sub in the third value. F of x2 equals C0 plus C1, x2 minus x0 plus C2, x2 minus x0, x2 minus x1. Okay, now we need to solve for C2, so we can sub in the value for C0 and C1. So C0 is f of x0, C1 is f of x1 minus f of x0 divided by x1 minus x0 times x2 minus x0 plus C2, x2 minus x0, x2 minus x1. Okay, I'll spare you the effort to do that computation for C2. I'm just going to write down C2, but you can basically rearrange. So for example, you can move the f of x to the other side, and then do simplification to compute C2. I'm going to write the formula for C2. And this is written in such a way that we can actually generalize this. Okay, so f of x2 minus f of x2 minus f of x0 divided by x2 minus x0 minus f of x1 minus f of x0, x1 minus x0, the whole thing divided by x2. I'm going to correct myself. There is an error here in this equation. Got it incorrect here. So it's x2 minus x1, and then this will be, this looks right. Okay, and then the bottom one is x2 minus x0. I need to correct this in my notes. Okay, now here's the thing. This part of the formula looks similar to the one here, the slope. Right? It's basically the difference between the y coordinate divided by the difference on the x coordinate. So what we'll do is we'll create our own notation for the slope. We'll denote that as, let's say, capital F x2 comma x1 minus capital F x1 comma x0 divided by x2 minus x0. Okay, now the notation we've used here is something which we created, just a shorthand notation, which helps us to keep track of lengthy expressions. But capital F xij is small f xi minus f small xj divided by xi minus xj. Yeah, it's uppercase. This is lowercase. Lowercase, this is uppercase. Okay, to summarize, that is, I'm going to summarize all the constants we've got. We have 3 constants in this problem. Those were as follows. C0 was f of x0. C1 was small f of x1 minus small f x0 divided by x1 minus x0. And then we could potentially write this as capital F x1 comma x0. This is our notation which we just created. C2 was, I just have it right up there. It's capital F x2 x1 minus capital F x1 x0 divided by x2 minus x0. So what we can do here is, just to create another shorthand notation, and I hope this becomes obvious, is we can denote this as capital F x2 x1 x0. Okay, so that's the three constant. But here's the thing: if you just keep doing this for 4 points and 5 points and 6 points, you can just generalize this formula. So for 2 points, the formula has C0, C1, C2, where there was small f, capital F with two so small f has one argument, capital F on line 2, C1 has two arguments, two inputs. The third one, C2, has capital F again, but 3 input arguments. So if you go C3, you will just have F with 4 arguments. I'll write that down. And then we can just generalize it to n dimensions. So as we increase the size of the polynomial, we can generalize the formula. So for this, for C3, it will be capital F x3 x2 x1 minus capital F x2 x1 x0 divided by x3 minus x0. By the way, this can be written as capital F with 4 arguments: x0, x1, x2, x3. So we keep doing that till, say, Cn, which will be f xn, xn minus 1, so on till x1, minus capital F x n minus 1, capital X n minus 2, so on till x 0 divided by x n minus x0, which can be written in a form this way: x0, x1, so on. I should reverse the order. We just stick to one convention. Hold on, let me see. Okay, I reversed the order, so I should just reverse this just to be consistent. This should be written as x3, x2, x1, x0. And this would be just to be written in the reverse: xn minus 1, so on till x0. Okay, and the equation which we are really interested in is f of x equals f of x0 plus x minus x0 capital F x1 x0 plus x minus x0 x minus x1 capital F x2 x1 x0. And this keeps going till we reach the last term, which is x minus x0, x minus x1, so on till x minus xn minus 1, capital F xn, xn minus 1, so on, like 0. Yeah, only this is a lowercase. Let me just put down. Okay, so what we'll do is we'll actually simplify this even further. In fact, what I'm going to show you is uh, the the kind of calculations which go with this are really, really simple, because I'm going to show you a simplification to these formulas if you know something about the structure of the data which is coming to you. So if the data is uniformly spaced, that is x0, x1, x2, x3, so on, are on a uniform grid, like 0. X0 is 0, x1 is 0 0.1, 0 0.2, 0 0.3, 0 0.4, then this formula actually reduces to something really very simple, and then you can do the math really quickly. So I'll show that to you, and then we'll just use that for our example problem. Okay, so we're going to look at simplification to Newton divided difference for uniformly spaced points. Okay, that is, if xi was x0 plus I delta x, where I was 0, sorry, I was 1, 2, so on till n, then these formulas simplify in the following way. C0 is simply f of x0, what we wrote down. There's no change to that. C1 we wrote down as f of x1 minus f of x0 divided by x1 minus x0. But that is the differential of f, which is saying that delta f here is f of x1, f of x0. C2, if you take the formula and simplify it, it comes out to be f of x2 minus twice f of x1 plus f of x0 divided by 2 times delta x square. Okay, that is just taking the formula from the earlier page and then just crunching in the values for uniform grid. But if you recognize that expression there on the right side, it's basically the second derivative of f at x0. So that's basically delta square f0. I'll write that 2 as 2 factorial delta x square. Okay, so we can keep doing that till we end up with Cn, which is capital F xn, xn minus 1, all the way to x0. This actually can be shown that it simplifies to the nth derivative using finite difference, of course, n factorial delta xn. Okay, so this gives us what is known as the Newton-Gregory forward interpolation formula. Here the formula is given as follows. Y equals f of x is f of x0 plus delta f0 delta x minus x0. Next term is delta square f0 2 times delta x square x minus x0 times x minus x0 minus delta x. And then this keeps going till delta n f0 n factorial delta x raised to n x minus x0 x minus x1 all the way till x minus x0 minus n minus 1 delta x. Okay, yeah. It's this f or this f.
Yeah, that one.
This one, second one.
Yep.
The second one is this.
Oh, okay.
The difference.
Okay. Thank you.
Yeah. And then this one is the difference. And this is probably very complicated. I won't even try to write it down, but I'll show you a trick on how to do this without actually having to write down these formulas. So this formula is only for information. We'll just get those values by doing a trick, which I'll show you in just a bit when we solve a problem. Okay, now it turns out that you don't have to be restricted with just the forward derivative, the forward difference. That's f0 is the forward difference, right? F of x1 minus f of x0 divided by delta x. You could also do the same thing with backward difference. So that derivation I'll skip, but that formula, which I'm going to write down next, is called the Newton-Gregory backward interpolation formula. Okay, it'll have a form which looks very similar to this. This one is based on f of x0, but that will be based on f of xn. So let's look at that one, and then we'll solve a problem which will just tie everything together. So Newton Gregory backward interpolation formula. Okay, so it goes something like this. Y equals f of x equals f of x n. So getting the value at the last point, xnth point, plus del. This symbol is called del or nabla. Del f of n delta x minus xn plus del square fn 2 factorial delta x square x minus xn x minus xn minus delta x plus, so you keep going like this till you reach the last one. That will be del n fn divided by n factorial delta x raised to n. And then we'll have a string of polynomial xn x minus xn minus delta x, so on till x minus xn minus. My bad here. This should be plus, by the way, because xn is the last point, so you need to add to it. Xn, this will be plus, and then plus n minus 1 delta x.
the end there. Is that like a continuation, like dot, dot, dot?
Yeah, dot, dot, dot. So this is the second term, then there'll be third, fourth, fifth till nth term. Okay, let's do a problem, and I promise you it's much simpler than what it looks like. It's not that hard to do this calculation. We'll not even look at that formula. We'll get it without looking at the formula. Are those two dots? Yes, that's the dots are indicate terms from 3 to n minus 1 because the nth term is here. Okay, so let's do a problem example. So consider the following data points: 0, 1, 2, 3, and the corresponding y terms are 2, 0, 4, and 20. Okay, so 4 points. Okay, the question is, A, use Newton-Gregory forward interpolation to fit the data. B would be use Newton-Gregory backward interpolation to fit the data. C is estimate the value of y at x equal to 0.5. Okay, so it's no, just estimate at 0.5. So what it means is, you know the data, you know something at 0, 1, 2, 3. We want to, and so clearly at 0 it's 2, at 1 it is 0. We want to know what happens in between this at 0.5. What's the value of y? Right? Now you could guess, you could say 0 to 1, it goes from 2 to 0. So if you, a good guess would be 1, right? Right? Because if you assume it's a straight line, you can just look at, say, it's 0.5. But if you look at the other data points, you'll see that 0.5 is not a good estimate because you're ignoring the other data points. So we'll see what the value is using this interpolation. By the way, you could do the same problem with other methods I talked about. Okay, so let's see how to do this. X, f of x. So this is how you will do this. You will create a table. So x is 0, 1, 2, and 3. F of x, I just copy it down, 2, 0, 4, and 20. Okay, now delta f, okay, is as simple as subtracting this from this. So 0 minus 2. This would be 4 minus 0, 20 minus 4. Okay, so I've put those calculations down the way you don't have to really write 0 minus 2. You can just put minus 2, that's fine. Delta f square. Now, delta f square is built off from delta f. So you do the same thing with delta f. 4 minus minus 2 equal to 6, and 16 minus 4 equals 12. Okay, it's clear, this 16, this 4. Then we go delta, it should be delta cube f. 12 minus 6 is 6. Okay, now we come to the formula. The formula is y equals f of x equals, so this is how you'll proceed. Just look at the top line. This, 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 and this. And then just keep putting it down in that formula. So it'll be 2, that's f of x, 0, plus delta f minus 2 divided by delta x, which is 1, right? Delta x is the difference between these two. It's 1 minus 0, 2 minus 1, and so on. So this is delta x. It's the same thing, right? So the gradient, it's a uniform gradient. So that's delta x, which sits down, times x minus x0, but x0 is 0, right? Plus, so I took this, I ran with this, and it's come to 6. 6 divided by, so what you'll have here will be 2 factorial, delta x square, so it'll be 1 square times x minus x0, so x0 is 0, x minus x1, which is 1. Then we have 6 divided by 3 factorial, 1 cube, x minus x0, x minus x1, x minus x2. Okay, where did these numbers come from? They came from, we put a different color here. This came from something like this part, and then the other parts. But you hope you get the idea that you really don't need to look at the formula. Once you know the pattern, it's just a matter of putting it down in the right way. Okay, so you can simplify this. Let's try to do that. So it's 2 minus 2x. Okay, so let me write the simplified form. That's 2. Then we have minus 2x. This thing will be 6 divided by 2 would be 3. 3 times x minus 1 will come out to be 3x square minus 3x. Then we have this. This thing is, I can just do this multiplication here and get x cubed minus 3x squared plus 2x. That's just this part. But that is to be multiplied by 6 divided by 3 factorial. 3 factorial is 6. So 6 divided by 6 is 1. So this just carries over here. So plus x cubed minus 3x squared plus 2x. Okay, we can cancel a few things, I believe. This 2x cancels with this plus 2x. This 3x squared cancels with this 3x squared. And that's it. So the final answer is y equals x cubed minus 3x plus 2. Okay. Okay, now let's do it using the backward interpolation formula. Okay, we'll do a similar trick. We don't have to really use the formula in that detail. Once you know the pattern, it's easy. So let's recreate this table for the backward interpolation. So part B, x 0, 1, 2, 3. F of x is, I believe, 2, 0, 4, and 20. Now we do del f. Now the way you do it is you start from the bottom. So 20 minus 4 is 16. 4 minus 0 is 4. 0 minus 2 is minus 2. Then we have delta square f. We start from below. 16 minus 4 is 12. 4 minus of minus 2 is 6. And there's nothing more to more calculations. Then del cube f is 12 minus 6. 6. Okay, again, you don't have to write these calculations in this much detail in the exam, just or in the homework. I'm just writing it down so that when you refer to the notes later on, you're not confused where it came from. Okay, now for the backward interpolation, we only have to look at the values here down. Okay, so that formula is like as follows. First is 20, and it doesn't have anything. It's the constant part of the equation. Then we have plus the next one, 16 divided by delta x, but delta x is 1 because the same difference. Delta x is 1 minus 0 and so on. Plus 12. Oh, I'm forgetting something. I should have x minus xn, but xn is 3. It's the last value. Plus 12 divided by 2 factorial delta x square x minus xn, so that will be 3, x minus xn minus 1, so it will be x minus 2. Okay, so let me continue this on the next line. Then we'll have 6 divided by 3 factorial delta x cube. Then we go x minus 3, which is x minus xn. Next one, x minus 2. Next one, x minus 1. Okay, so we're left with only simplifying this expression. +16 x minus 48 plus 12 divided by 2 is 6. X squared minus 5x plus 6. The last one would be 6 divided by 6 is 1. And then we have x minus 3. I'll do the first two terms. So x squared minus 3x. So x squared minus 5x plus 2 times x minus 1. And if you expand this out, I think you get square minus 5x squared plus 6x, then minus x squared minus. Yeah, I just did it in my head, but this is what you can expect when you expand this out. 6x square minus 30x plus 36 plus x cube minus 5x square plus 6x minus x square plus 5x minus 6. There's 6x square here, and then 5. So I think this, and this cancels off. This carries over. X cube. Okay, then we can see x square all get cancelled off. You're left with 16x minus 30x. That's only minus 14x plus 6, so minus 8 plus 5. So 3 minus 3. Very good. Okay. And then last one, 20 plus minus 48 minus 24. So minus 24. And then 36 minus 6 is 30. So this comes out to be 6. This is 6. That doesn't look right to me. No, this is wrong, right? This is not 24, it's 28. 20 minus 48 is 28, and then 30. So I think it comes out to be 2 plus 2. Yeah, question.
Yeah, so just real quick, can you go back? Yeah, just the like where you put like the x minus 3, where exactly you meant, or is that just like you started?
You start from here and you go upwards.
Oh,
Because this formula, yeah, if you look at the formula, the backward formula, you always start with the last value, xn.
okay.
Okay, so what we see here is something interesting, which is if we look at the solution I got for the, so this is part A. This is the solution obtained using forward interpolation. Okay, x cubed minus 3x plus 2. We did this with a different method, different formula, backward, this is part B. So backward interpolation, you get the same answer, x cubed minus 3x plus 2. So you should expect the same answer no matter which formula you use. The last step is to evaluate y at 0.5. For that, you just put 0.5 cubed minus 3 times 0.5 plus 2. If you do the math on that, it comes out to be 6.25.